Okay, hi everyone. Welcome to another week, another Flan Talk. This week by Chenxiao, a PhD student at TTIC. He's gonna present the work Pencil, Long Thoughts with Short Memory. Okay, go ahead. Thank you.
Uh, so is it working correctly? Like what?
Yeah, yeah, I can see
Okay.
it. Oh.
Hi. Good morning. I'm Chenxiao from TTIC. Today I will share our recent paper called Pencil Long Thoughts with Short Memory. Oh, what happened? This is a collaborative work with Professor Nathan Srebro, David McAllister, and Juan Li. So here is a brief recap of chain of thought. So chain of thought, like we know, so without chain of thought, we language models generate the answer directly, but using chain of thought, it generates some intermediate reasoning steps before answering the question. And this has been a technique used in many language models, and it has been shown in many previous papers that using chain of thought can dramatically increase the reasoning performance of these models. So here is some results shown in the ARC-AGI benchmark, where here is the performance of OpenAI O1 and O3. As we can see, the x-axis is the test time computes, and the y-axis is the score they can achieve. By using more test time computes, they show that the performance can get dramatically better. And there is also some reproductions in academia how to using longer chain of thought to generate to increase to get better performance. And as we can see here in three mathematical reasoning benchmarks, the using more thinking time and by generating more tokens, the accuracy can get dramatically better. So there are also some theoretical results showing that longer chain of thought can empower transformers to solve computationally more intensive tasks. So the key, so during the this is how chain of thought is implemented in practice. So given a question, we use a language model or a transformer architecture to generate the next tokens. And when we generate net token, and when the next token is generated, it will be appended to the previous sequence, and we keep iteratively doing so until we get a final answer. So one key property of this process of this autoregressive property of this autoregressive model is that the thoughts will never get erased. The tokens will the generated thoughts will stay in the context forever. So, but this will introduce as we are solving more and more complex tasks and using longer and longer chain thought, this will introduce many problems. For example, when if we want to solve some tasks, for example, consider like solving some NP hard tasks where we might need to generate exponentially many tokens, it will easily run out of memory. Because like for language models, the context window size is limited, and when the current sequence length will exceed the context window, the window will slide and only contain the most recent a few tokens. And in this way, the earlier tokens will be just buried, will just be discarded, and maybe there might contain some important information. This will like hurt the performance. And another issue is like when the current sequence is too long, generating because we know self-attention takes quadratic complexity, and when the sequence becomes too long, generating each token would be prohibitively expensive. And also because even we can fit the whole sequence into the attention window context, and even we can like generate a very long thought. There are some recent works showing that there might if there are too irrelevant information in the current sequence, it might be very hard for language models to retrieve the useful informations within those uh, irrelevant context, irrelevant information, right? But one key observation is that for human reasoning or like for LLM reasoning, most intermediate steps are actually erasable when they are used. So consider proving a theorem. There are infinitely many prime numbers. So how do we prove this? To prove this, we might need some lemmas, or like for every integer, and have every integer has a prime divisor. So to prove this theorem, we might prove the lemma. And when we know that when we know that this lemma is correct, we no longer need the proof of this lemma. We only need to use this lemma itself. So in this situation, we can just erase like the proof the lemma is no longer useful for the following reasoning process. Another example is like it's generally true like for other problems like for LM reasoning. Consider a question which is from DeepSeek R1's round. The question is like your mother had four children, north, south, east. What's the fourth child's name? So initially, like the model might explore different ideas, and the language models might generate something that is like it might answer the first child's name is West, but then it realized this might not be correct because like it asks it might be a trick because your mother means you are the first child. So the correct answer is your name. But so when it explores different strategies, the previous strategy might just the reasoning process is actually no longer useful for the following reasoning process. So this intermediate step is also erasable. And the idea of erasing the thoughts is fundamental to modern computation for any computational models. We can think of one step of thinking, generating one step of thought as one step of computation because like essentially transformer is a computational model and generating one step of a token is like doing one step of computation. And if we consider analogy between like transformers and existing computational models, we see there is dramatic difference. From the earliest Turing machine, it can rewrite it can rewrite the tape when it knows that some symbols on the tape is no longer useful. And like for modern computers, we store some informations, variables in the memory, and when this variable is no longer useful, we just erase it and replace store some other things in the memory. But nowadays, like using transformer and the chain of thought, it never like it only generates the thought and keep the generated thought in the memory forever. And this is just like a pen. We keep writing the thought, but we keep writing the thought on a blank paper, but we never erase the thoughts. But this is fundamentally problematic. This is a terrible. If we think of it as a computational model, this is a terrible computational model. In this paper we propose pencil, which can not only write the thought but also erase the thoughts. So what does pencil mean? So it's a shorthand of pencil enables context-efficient inference and learning as the name suggests, it's more about the efficiency using limited resources to generate longer thoughts and to address more complicated problems. So what is pencil? Just like chain of thought, it can write, it can generate tokens and generate thoughts. But the key point of pencil is like it can not only generate the thought but also erase the thoughts. But there is no such mechanism within the autoregressive net token generation paradigm. There is no such erasing mechanism. So how do we do this? we take inspirations from functional programming language. So in functional programming language, the way it manages the memory is like when it solves some kind of problems, it can call another other functions, and when it calls another function, it creates a stack frame, and the all computations within the new function is stored in that stack frame, and when this function returns, it will just erase the stack frame and only return the value because um, we know that the information stored in that in within that function is no longer useful for the following computations. So this is how the way we introduce the erasing mechanism in Pencil is similar to the functional programming language. So how do we do this? We use a simple reduction rule. Here, C refers to the context, which is a subsequence, and T refers to solves, the intermediate computational steps, and A refers to the answer. And we also introduced three special tokens, which is called call, step, and return. So the model is allowed to generate these special tokens. And whenever the current sequence matches this pattern, it will trigger the reduction rule and will erase the sort along with these three special tokens and will merge, and the model will automatically merge the final answer into the context. So and overall, Pencil will iteratively generate sorts and trigger reduction. So here is a simple example of how Pencil might address a simple arithmetic expression evaluation question. So the question is like this: a toy store put together party bags for a birthday. They made three blue bags with 5 toys each and two red bags with four toys each. And how many toys were used in total? So how does Pencil address this? So this is a simple question, but we can decompose this question into sub questions. So we might want to know there how many toys in red bags. So by some simple calculations, we know there are 15 toys in blue bags. And when we know the final answer, it will trigger the reduction rule. So it finds when the current sequence has a return token, it will find the most recent SAP token. And when we find the SAP token, it will find the most recent call token before that SAP token. And this is a pattern in the current sequence, and it will trigger this reduction rule to eliminate to delete the intermediate thoughts, and will merge the final answer. There were 15 toys in our blue bags into the context, but this is not done. The model will keep generating new tokens, so it will use another call token to solve another sub question, which is how many toys in red bags. So after some simple calculations, it knows there are 8 toys in red bags, and it will merge the results back into the context. And when we know the answers of these sub problems, we know there are totally 23 toys in 23 toys, and it will merge the final answer back into the context. So this is how Pencil works. It will return the final answer without keeping the intermediate thoughts. So here is an animation of how Pencil addresses this problem. It will iteratively generate the thoughts and erases the thoughts. Here is a summary of how it comparing chain of thought and Pencil. This is the question we just mentioned. And for chain of thought, it will generate the entire reasoning process and getting the final answer. But for Pencil, it will only return the answer. But before giving the answer, there is an iterative generation and reduction process, which is the hidden COT here. Like it works just like you can think of it as like it works just like OR models. it gives a concise answer, but there is a hidden COTA reasoning process uh, before giving the final answer. So to better understand how pencil how effective is effective it is like compared with the chain of thought, how efficient it is, we can consider a very difficult example called quantified Boolean formula, which is a piece-based complete problem, meaning that there is no based on common assumption, there is no exponential there is no polynomial time algorithm to solve it. We can only the exhaustive search is unavoidable. So the question is like that. The question is like, for example, there is a Boolean formula, and we want to answer if there exists such a value assignment for variable x2 and variable x1, for such that for any variable x1, the Boolean formula is true. So how do pencil solve this? There is a very naive algorithm to do this. We can just try different value assignments for each different variable and see if it meets the requirement. So we might want to decompose. We don't know the answer of this question. It's very complicated. So let's decompose this question into sub problems. Let's first try x2 equals to false, which is a simpler question because we can just substitute the value false into this Boolean formula, and this is a sub question. And still, we don't know the answer. So let's try x1 equals to false, which now we can calculate. Now we can calculate if the Boolean formula is true. We can so it is false. And when we know the answer is false, we will just eliminate the intermediate results. And because it says for any because the question is like for any x1, it's if the Boolean formula is true, and we already know if the x1 is false, the answer is false. So we know that for if x2 is false, the answer is false. So we can just eliminate the reasoning process. And let's try another value assignment for x2, which is try x2 equals to true. And after some calculations and try x1 equals to false, the answer is true. So we keep the result. Let's try x1 equals to true. The answer is false. And when we know the because there exists such a value assignment for x1, the Boolean formula is false. So the final answer is false. So for both value assignment for x2, the answer is false. We know the answer is false. So this is how pencil works in in the QBF example. So the reason why I mentioned this example is that there is for chain of thought, solving this problem, like you have to try different value assignments for different variables. The maximal context length is exponential to the size of the problem. So the size of the problem is defined as the number of variables in this Boolean formula. In this case, n equals to 2. And there, for chain of thought, the maximal length is proportional to exponential n. But for pencil, the maximal context length here, as we can see in the previous demonstration, it's just linear, and which is the depth of this binary search tree. And maybe when the size of the problem is not too large, the difference is not so significant. But when the size of the problem becomes very large, when there are, for example, 10 different variables, the maximal context length comparison between train of thought and pencil is very dramatic. Like there is like the difference is like 0.004. And then in another example, which is a easier problem, which is a NP complete problem, three that the difference is also dramatic with the size of the context length of the for chain of thought grows exponentially, while the context length for pencil just grows linearly with respect to the size of the problem. So imagine using imagine using using this slide to solve the QBI problem when the size of the problem is n equals to 10. This is the thoughts used for chain of thought to solve this problem. This is the space that will be used by chain of thought. But for pencil, this just like it can use a very tiny space to address this very complicated problem. So how does pencil perform in practice? How does it compare with train of thought? So before introducing the results, we might let's first introduce the experimental setting during training and inference. How do we train pencil to not only generate the thoughts but also erase thoughts, and how does it behave during the inference time? So the key difference between chain of thought and pencil is the data generation process. There is no difference there. Otherwise, there is almost everything is identical to chain of thought. The only difference is just how the data is generated. So for chain of thought, there is like no special tokens, but for pencil, we will introduce these three special tokens because by introducing these three special tokens, call, accept, and return, it will trigger the reduction rule and do the erasing. So, and also the computation of loss functions is different. For chain of thought, the loss function is calculated for each token. The loss function is calculated based on all previous sequence, which is very long. But for pencil, the loss function on each token is calculated based on the reduced sequence, which is much shorter compared with the complete sequence. And we train in our experiment, we train a very small transformer with only like 25 million parameters and 2000 context lengths from scratch to compare their performance. And during inference, whenever we trigger this reduction rule that eliminates the thoughts, we can preserve the KV cache of the context part, and we only need to recompute the KV cache for the answer part because when we merge the answer into the context, the position its position will change, and we might need to recompute the KV cache. So, but compare with the context, the computation is marginal, so it will not introduce so much additional computes. So here is the performance comparison between 3-that and QBF. N refers to the size of the problem, meaning the number of variables for these two problems. And the baseline means not using chain of thought. We train the model to directly output the answer. And the chain of thought is it uses the same reasoning process as pencil, but without using the reduction rule. It doesn't eliminate the thought, but generates exactly the same reasoning trees as pencil. So as we can see from this table, when the size of the problem, when n is not too large, the performance of both chain of thought and pencil both of them can achieve almost perfect performance, whereas the baseline, the performance is very low. It's just like random guessing. But when the size of the problem becomes very large, for example, when the size of problem becomes 10, the performance of chain of thought degrades dramatically, and the pencil can maintain almost perfect performance. This is because when the size of problem becomes very large, it might need the context length requirement for chain of thought will grow exponentially. But in practice, we don't have so many resources don't have so much space to contain all the reasoning, all the thoughts. So the performance of chain of thought will degrade dramatically. But pencil, because the context length requirement only grows linearly, so it can still solve these problems perfectly. We also compare the convergence speed of chain of thought and pencil. This figure shows how during the training process, how the accuracy of chain of thought and the pencil, and how the training laws converges throughout the training process. As we can see, for so the blue color refers to chain of thought and the red color refers to pencil. And use when trained on the same using the same amount of training data sets trained on the same amount of tokens, pencil can converge faster to almost perfect performance, but while chain of thought, even using the same amount of training set, it converges slower. It means that by discarding the irrelevant information in the context, pencil can learn to reason more efficiently. And because like for generating each token, the prefix for pencil is dramatically smaller than the prefix for pencil, meaning that to compute each token, the amount of computes for pencil is significantly smaller than pencil. So this means we can, even if we change the x-axis in the previous figure to the amount of computes, then the difference between these two approaches is even more dramatic, meaning that using the same amount of compute, pencil can even converge significantly faster than uh, chain of thought. And when the size of the problem becomes large, the difference is even more dramatic. So here we will introduce another example and evaluate on this example. This problem is called Einstein's puzzle. So the problem is like that. In the prompt, it will give it consists a set of constraints, and the task is to fill the table below. There are, like in this example, there are 3 houses, and we don't each house has a unique color and the nationality of the person who lives in this house and the pet who is unkept by the person living in that house. But we don't know the color of that house and we don't know the nationality of the person living in this house. So given this a set of constraints, we might want to fill this table and answer the question, who owns the fish? And we want to train the language model we want to train a transformer to solve this problem, like in a natural language reasoning problem, and fill this table to answer the question, who owns the fish? It's claimed that 98% of the world's population cannot solve this problem. The original puzzle has 5 categories instead of 3 categories shown in this slide. So I've done this task myself. It's very difficult to do this. So here is how pencil address this problem. Like for each constraint, we can consider each constraint as a subproblem. And by considering each constraint, we can, the high-level strategy is to, based on each constraint, we want to infer what are the possibilities to fill in this table. So after reasoning about each constraint, we can update the possibilities to fill in this table. And when we know what are the remaining possibilities in this table, we can eliminate the reasoning process to get this result. And when we have considered all constraints, meaning that when we have solved all these subtasks, we can summarize what are the remaining possibilities we can fill in this table and summarize these state changes and update the possibilities. And this will eliminate all the previous thinking process. We only keep the final answer, that like the summary of the previous thinking process. And still, when the problem is not solved, we don't know how. For example, we don't know, there are 2 possibilities to fill in for the color category in house 1. For example, it could be a red house or it can be a blue house. We might want to try different. We might want to try these different possibilities. For example, we might want to first assume the first house, the color of the first house is red, and this will create a branch. And when the language model do the reasoning process and know the final answer is like when the color of the first house is red, it will lead to some contradictions. Then it will use the our reduction rule to eliminate all the reasoning processes and only keep the final like only keep the answer that the possibility that house one is red is not possible, and it will just eliminate the entire reasoning trees and try another possibility that is if the house one's color is red is blue. So here is how like how pencil can solve Einstein's puzzle. So here we use another trick how to use this reduction rule. That is, it can do summarization. Here, T refers to a very long thought. You can think of as, for example, when it generates after a long time of thinking, when it still doesn't get the answer, but there is a very long thoughts accumulated in the current context. We can just, but not all thinking processes in these long thoughts are useful. So we can use this summarization. We can summarize the previous thinking process into a summarized thoughts, which is T prime here. So it triggers the reduction rule and only keep the new summarized thoughts. So this is inspired like by tail recursion in functional programming. Consider like, for example, when we the returned value of this function here is like an example of computing the factorial of a certain number. It's not just a returned value, it returns another function call. The returned value is another function call. So here the answer is just a call t prime. So it means that the returned answer itself is a question. You can think of it as a for example, there is a very complicated question, and after some thinking processes, it transforms this complicated question into a more manageable, simpler question. So this is how like summarization works. The reason why I mentioned this is because in the following, when I introduce the following theoretical results, we will use this reduction rule, right? So here is the performance on Einstein's puzzle. When the size of the problem, when the table size is 5 by 5, the performance of chain of thought is near random guessing because even if you just random guessing, the accuracy is 20%. But for a pencil, the performance can be almost perfect. And I'll note that even like we have tested on like state-of-art GPT, like state-of-art language models like GPT-4, it cannot solve the original Einstein puzzle perfectly. But in our experiments, we only use a very small transformer to train on this very challenging test. It can like even outperform state-of-the-art language models. This is very impressive result. And even when the size of the so the reason why it can achieve such impressive performance is because like for if we use train of thought, the number of tokens we need to generate to solve this puzzle is like one 150,000 many tokens, but for pencil it's just 3,000. It's like dramatically different. And even when the size of problem is very small, like even if it's just even if there are just three categories, we can see that in this figure where the we compare the performance of chain of thought and the pencil using different context lengths and using different models of with different number of parameters, we can see that pencil can use much smaller context lengths to solve this problem perfectly. But for chain of thought, it requires a larger context length to solve this problem. But in terms of the number of parameters, as we can see, as long as the size of the model exceeds a certain threshold, both chain of thought and pencil can address the problem. So the key bottleneck here is not about the number of parameters. Also, we compare the test time scalability of Pencil and Chenxiao on these problems. So these figures, the x-axis is the by like given the different inference time budget, and we consider the size of problems Chenxiao and Pencil can solve. So as we can see from this figure, where like the blue line refers to train of and the red line refers to pencil. Given more inference time budget, chain of thought, there is limit of test time scaling. Like for chain of thought, even given more inference time, the size of the problem they can solve has a limit. It even with infinitely many inference time, it can only like for on QBF, it can only solve QBF n equals to 5, but for Pencil, it can solve significantly more challenging tasks using the same amount of space and this using the synthesized model. So another question is like, how about other tasks beyond these examples considered in our experiments? How about other general reasoning tasks in math and in like for biology or whatever other computational tasks? How well can pencil solve compared with like how well can chainsaw solve? So next, we want to ask a theoretical question about how powerful is pencil. So, the result is pencil can perform universal computation, both space and time efficiently. So there are some previous results showing that with transformer, chain of thought is Turing complete, but meaning that it can solve all computable tasks, but this is done inefficiently. So here is the result in to prove the chain of thought is Turing complete. Like for any Turing machine, there is this finite size decoder only transformer such that chain of thought with this transformer simulates the Turing machine with total number of generated tokens equal to the maximum context length, which is the number of steps. T here refers to the number of steps for a Turing machine, which is like the time complexity for solving that problem. This is because because Chenxiao never erases the thoughts, so the total number of tokens is equal to the maximum context length. So here is how to give a high level intuition how to prove this theory and like how to understand why chain of thought though it's very powerful, but why it's inefficient. So for the left figure shows the behavior on a Turing machine's tape, where for each transition step, it produces the next state and the symbol written on that tape and the movement of the head. And to encode this single transition step, we use for chain of thought, it generates a new token, which is a triplet of the state and the symbol and the head movement. So for each step of computation for Turing machine, chain of thought will generate a new token. So the number of tokens generated is equal to the number of steps used by Turing machine. And then eventually, when we find that even though Turing machine only writes 4 symbols on the tape, for chain of thought, it might generate more tokens than the space actually needed to solve this problem. So this is problematic because like if you think of it as a computational model, then the space actually needed is far from the optimal. So this is how Pencil can make the improvement. This is the theoretical results for Pencil. It states that the statement is like for any Turing machine, there exists a finite size decoder only transformer such that for any input on which Turing machine uses T steps and S space to compute, Pencil with this transformer computes the same output with the total number of generated token is equivalent to chain of thought, which is the time complexity for solving this problem. But the maximal content length is significantly smaller, which is the space complexity for solving this problem. It means that like for most problems, the time complexity to solve this problem is usually significantly smaller than the time complexity. For example, like for those NP hard problems, the time complexity is like only like polynomial to the size of problem, but the space complexity is polynomial, but like for time complexity, it could be exponential. So the implication is that Pencil can solve any computable tasks efficiently with optimal time and space complexity. This is previously impossible without the reduction rule, without erasing the source. So here is the implication. We can consider a specific example. Like we know, like in real world cases, the space is limited. The memory we can use is limited. So let's assume we can just use a polynomial context length to solve problems. So what can Pencil solve and what can chain of thought solve? So for Pencil, it can solve all problems in P space, while standard chain of thought can only solve problems in P. So P here refers to the problem solvable in polynomial time, and P space refers to the problem solvable using polynomial space, regardless of how much like test time we use during inference. So the implication here is complex complexity hierarchy for like pencil and the chain of thought. This means that for like in real world cases, even if we allow infinite amount of test time compute, because of limited resources in memory, chain of thought can only solve problems in using polynomial time. It means that beyond this, even if it allows to use more test time compute, it cannot solve more harder problems. But for Pencil, it like can solve these more complicated problems beyond the P. Like it goes to like NP and the P space. So here is like high-level idea how Pencil can achieve both the time and the space optimal. So for chain of thought, as we mentioned earlier, each step of computation refers to one transition step of Turing machine. So the total number of generated tokens and the maximum context length is equal to the time for solving this problem. But for Pencil, it uses a different strategy. They can iteratively think and summarize. So here, step just means simulating one step of computation of Turing machine, and the state means using a set of tokens whose size is proportional to the space used in Turing machine to keep track of the current configuration of Turing machine. So here from the previous state, which is proportional to the space used by Turing machine, and Pencil can generate a few steps to simulate the computation of Turing machine. And when the current length of the sequence exceeds a certain threshold, it will trigger the reduction, and it will summarize the previous thinking process into the current state, which means the current space occupied by the current space used on the tape. So in this way, it iteratively think and summarize. It will keep the final space used by the Pencil proportional to the space complexity of the algorithm. So, but another question is when to do summarization. There are like a few different strategies. When Pencil triggers the summarization. If it never triggers summarization, if it never eliminates the thought, it's equivalent to chain of thought, because like both chain of thought and Pencil in this case is just keep generating the thoughts. So the total number of tokens generated and the maximal context length, both of them is proportional to the time complexity for solving that problem. However, if we a naive strategy to the summarization is like whenever we generate a new token, we do the summarization. But in this case, or whenever we generate a constant number of tokens, we trigger the summarization. In this case, even we can if the maximum context length we can achieve optimal, which is the space complexity for that problem. But the trade-off is that like the time complexity for solving that problem is time times the space, which is not optimal because like compared with the baseline chain of thought. So the strategy we used here is like when the current context length exceeds twice the actual needed space, we do the summarization. In this way, we can prove that both the number of generated tokens and the maximum context length is optimal, which is the time complexity and the space complexity. So now we know the high-level idea how Pencil can solve like arbitrary computable problems, why it can achieve both time and space optimal. But the next step will prove is like how do real-world transformers automatically detect when to summarize and erase, and can transformers do the summarization and simulate the running process of the Turing machine. So but because this is a very complicated algorithm, as we mentioned earlier in the previous slide. So here is a proof technique we use. We develop a programming language which we call full access sequence processing. So here is the lemma. Here is an important lemma here. So for all programs written in this programming language FASP, it's equivalent to a certain a fixed transformer. So all programs in if there is the algorithm can be written in the programs in FASP, it can be expressed by a finite size finite precision transformer. So here is the proof, just a program. So a FAST program describes a process of constructing transformers. So here is a high-level idea of how the correspondence between a FAST program and the transformer architecture. So in the program, each variable just refers to a transformer, which is like doing what this transformer does in its forward process is like producing the result corresponding to this variable. And for each line of code, because each line of code is just a function taking as input some variables and outputting and producing another variable. So what it means for transformers is like it's an operator from some simpler transformers to a more complicated transformer. And when we return the final return the variable is just the constructed transformer we want to for expressing this algorithm. So because this whole program, because for this program, what this program does is just the iterative thinking and the summarization process we mentioned in the previous slide. So we find that there exists such a finite size transformer can express this algorithm. So to summarize, here are a few future directions and open questions. So because we have only run experiments on some small transformers to test if it can automatically learn to generate the thoughts and erase the thoughts. But how to incorporate the erasing capability into real-world large language model systems? This might need, for example, we might need to generate some data sets and fine-tune existing language models to learn how to erase because like initially language models don't know how to erase the thoughts. We might want to generate some data sets to cold start data sets for language models to learn how to erase the thoughts and like how to and maybe there might exist other approaches we can teach them to reason in such a structured manner. And another question is like that, does there exist other erasing mechanisms besides of the reduction rule we proposed in this paper? Does there exist other reduction rules or erasing mechanism that is even more efficient than pencil? But the improvement might just be, for example, like constant. And another question is like a more theoretical question. Are there any other perspectives from which theories in TCS can help guide practice? How can we use theoretical insights from TCS to develop more powerful models in practice that works better? So here are the takeaways in this project. We propose Pencil, which is a new LLM reasoning paradigm that iteratively generates and erases thoughts using the reduction rule, like it's using the simple reduction rule. And empirically, Pencil enables longer and deeper thinking. It can generate a longer chain of thought using shorter context and can scale up and helps the model to scale up to handle more complicated and harder tasks. And theoretically, we show Pencil is Turing complete with optimal space and time complexity, and thus can solve arbitrary computable problems efficiently. So that's all for the talk. Thank you for your attention. Okay, so
Thank you
are
so much.
there? Mhm.